So for a 10-minute talk, I had to decide whether to cut some slides out or talk quickly, and I chose the latter. So I hope you've all had coffee. So this speed update is going to be on intelligent information systems for tree crops, and this work has been funded by HIA. So I'm going to focus in particular on the work we've done in ground-based sensing with mobile ground vehicle robots like this one here. It has a whole combination of different sensors on board, but today I'm going to mainly talk about the laser sensors and the camera sensors and how we can use those to gather information from orchards. And we've predominantly focused on almonds and apples, though the technology is sort of applicable in many different areas. So the vehicle is fully autonomous. It drives itself up and down the rows of the orchards. In order to do this, we use actual laser scanners to work out where the trees are, and so the vehicle can then steer itself down the centre line of these rows. Whereas in broadacre applications, often you have GPS guidance. Here we don't need to use GPS at all, and that's really important because in an orchard context, the tall canopies tend to block the signal from the satellite that GPS relies on, and so GPS is not very reliable for this kind of application. So here we can do the autonomy just with the lasers, which makes it a bit more reliable. Now, as we drive along, we have another laser looking out to the side, and as we drive past all the trees, this is scanning those trees. And so we produce a big three-dimensional picture of the orchard. And I've coloured all the different trees differently here, and this is to illustrate that we have autonomous algorithms and software to process this data to work out where one tree finishes and the next tree starts. And this is on an almond orchard in this case. So that's it. That's important because even though we're just driving along, we can treat each tree individually in terms of how we analyse the data. So in an automated way, we can pull out the data belonging to individual trees. And this is an example of some geometric information about one particular tree. And from that, we can, using algorithms and so on, using software, we can derive quantities relating to the geometry of that tree, such as the volume of the canopy and other quantities. Because we're able to re-identify the same tree again and again when we visit the orchard, on subsequent visits, we can also analyse the performance of individual trees over time. And so we can measure things like the rate of growth, for example. So here, to illustrate that, each dot on this graph is one of 580 trees in a test site. And it's showing the change in the canopy volume from one year to the next year. And so, it's indicating essentially that in this case, the nonpareil trees have all kind of grown, which we'd expect because they're relatively young in this example. And so we can track that information. Why would you care? Because it turns out that the canopy volume is related. It might be obvious, but it's related to the yield that each tree produces. And so if you want to do things like yield prediction and yield mapping across an orchard, then you want to be able to discover this information about all of the different trees. So this illustrates, for example, the 3D map of this whole set of 580 trees. The two different colours are because we scan each tree from both sides and put that together to build up that picture. So because we know where each tree is, we've got the ability to pull out a photograph in passing, a photograph of every tree centred on the trunk of that tree. So you can think of it kind of like Google Street View for an orchard, this big database of images. And so we put together this big database where we can look at seasonal and historical kind of comparisons. So we scan at peak bloom, we scan at fruit set, and we scan just before harvest, and we do that multiple years running, and you gather this massive database where for any given tree you can pull out the photos of what it looked like at all these key stages. Because we're doing that for so many trees, obviously this would be an overwhelming quantity of photos to actually go through manually and reason about. And so for that, again, we apply automation in terms of algorithms and image processing. So we have software that extracts the relevant information that we want from these photographs. So in this case, you see we're classifying, finding where all the flowers are at the peak bloom, finding where all the fruit is in the image. And so we can derive from that a single number representing the flower density of a tree or the fruit density on that particular tree. And because we've done that for every tree, we can map those type of quantities. So for example, here's a map showing the flower density for each tree. Here's a representation of the same data, flower density. And here we did a scan on 2 subsequent days. And by matching up that data, we can actually see how the flowers are changing. So for each tree, we can see, is it increasing in flower density, or is it, decreasing? And so we can estimate where the peaks in the bloom were, and we can do that, and we see the differentiation for the different varieties here in the case of almonds. Now, this is something that almond growers do intentionally. They select their pollinator varieties intentionally to be either side of the main variety, so that they've got the greatest probability of having all the flowers out at the same time. But in a sense, this is kind of quantifying that that's actually working in this case. And here you can see that differentiation with the different varieties, the pollinator varieties spanning the main non-Perel variety. And you can do that for all the individual trees, and also look at the statistics as a whole for an orchard block. So it's really about kind of quantifying that and checking that things are working as they should be. Here's an example of a yield map where we put various pieces of this data together to work out how the yield is distributed on a tree-by-tree basis across the orchard. And you can see there's a lot of variability tree by tree, but you can also see patterns. For example, this region on the left here, where it's sort of a bit redder than everywhere else, that's a patch where there's kind of lower yield than average. Now in this case, the farm manager is aware of this problem with lower yield next to the main access road through the orchard. But again, it's about quantification. So from this kind of data, you can actually start to ask questions like exactly how many trees are being affected. And for those trees, on average, what is the reduction in yield in this area? And so you can start to ask questions like, if you could address that problem, how much more yield might you expect to get from those trees? And therefore, is it economically worthwhile doing something about this particular problem? Just quickly, this is applicable to different fruits. Example of detecting mangoes, lychees. I'll just skip past these. So here it is for apples, and we're driving along a row of Kevin's farm here with the cameras out to the side and running these algorithms to detect all the apples, which are shown in red on the right-hand side. And so we can produce counts of apples by finding all the circles. And then we can map this to estimate yield in the same way I showed for almonds. We can look at the sort of row by row yield estimates. So typically growers might do a post-harvest yield weight on a whole block to find out how many kilos and how many apples they got from that block. But in this case, we can go further and sort of start to look at row by row estimates. And Kevin kindly agreed to support this experiment by actually doing a post-harvest weight and count in his packing shed on a row by row basis, which wasn't easy for him to do. But we were able to use that to verify that the image-based methods were able to fairly accurately estimate this same quantity in a much kind of more easy way to do it. One thing that's interesting here is we can start to look at the value of this information, is that we actually saw something that we didn't quite expect in this particular orchard block, which was a decreasing trend in the yield row by row across the block. So if you look at this triangle here, this is kind of like telling you, that white space inside that triangle is kind of like the missing yield. It's the missing potential that this orchard block might have. If you could identify the reasons why the yield is, stronger in some rows and weaker in other rows, you can actually, if you could bring that yield up to the average or up to the peak performing rows, then the area in that triangle tells you how much more yield you might be able to get from this particular block. And so you can start to actually see that as the dollar value, if you like, of the information that you can get by looking at a higher resolution into the orchard. So I'm going to conclude by just talking about, just summarising the capabilities. So at the moment, the sort of technology can be used to do, per tree measurement, but with very broad coverage. So a real focus on the individual tree, but in a way that's quite efficient to map out to every tree in an orchard. And from that, we can build a big database with seasonal, historical kind of, digital records. And then from that, we can do the data mining to start doing, performance tracking and diagnosis. And the next sort of phase in this work is to even look at individual fruit, not just individual trees, and track the growth of that fruit. Start looking at issues relating to health monitoring and so on, and also to consider ways in which we could use this data, not just for decision support, but also automated treatments. So for example, say thinning in apples, to plug in the maps of flower densities into automated spray, variable rate spray control on spray rigs to reduce the amount of reduce the input costs in those processes. So we see that's where one of the key kind of future areas of value is going to be with this technology. So with that, I'll conclude.